In this class, we are going to discuss about Stokes Law first. So, Stokes Law basically tells us about the relation between line integral and surface integral. That means whenever we are facing any kind of problems in this EM theory, where we will require the conversion of line integral to surface integral, we'll use this Stokes Law. First, we see the mathematical expression of this Stokes Law. So let us write it. Mathematical expression that is given by closed line integral of any vector quantity dl, that is equals to surface integral of curl of that vector. This is the mathematical expression. So what are the things to notice here? One is closed surface in line integral, closed line integral. Another is the surface integral. So from line integral to we are converting it into the in terms of surface, and the reverse process also can be done. Another thing is that here we are using the curl of that particular vector or the quantity that we are using. So I'm coming into the details. So first, write the basics. The basics of Stokes law is that it actually relates line integral to surface integral. So this is important to remember, and the vice versa can be also be done, right? So and also now write the theorem. Let us study the theorem. That what is the theorem states. So the theorem states that circulation, you see this term, circulation of a vector of any vector field a vector. So circulations, as you can see, this word circulation is actually a term where the rotation, it is actually the rotation of that vector. So that is the reason why using this cross product, or actually the curl that we are using. So circulation of vector A around a closed path L is equal to the surface is closed surface, L is equal to the surface integral of the curl of that vector of, here it is vector we are defining as taking as a vector, over over a surface, or rather I'd like over an open surface S enclosed by L, provided that vector A and curl of that vector A are continuous on that surface S, right? Or mathematically we can write mathematical expression, you can see the same, that is line integral of that vector A dl is equals to surface integral of curl of that particular vector. So now what it says, that the circulation of a vector field A around a closed path. So let us explain what it is saying. So we are simply drawing a figure like this. Say this is a line represented by the line. Here is the line. Suppose this is your point A, this is B, this is C, this is D. So our line L or path L is actually starting from the point A, it is coming to B, after that it's going to C and then D, and again it is being closed at A. That is, a closed line is being drawn. Now suppose any kind of field that is incident over this surface, be it a electric one or a magnetic field, whatever it is. So if this is the scenario, so then the line integral or closed line integral of that particular vector that is incident on it, be it an electric or a magnetic one, any vector, so you can take this vector as A inside it. So this will be equals to the curl of the surface integral of that particular vector. Why? That means It's very simple to understand. Since say we are starting from this A, now we are going to this B and C and then D, then again coming back to A. So what it means, the vector we are calculating, the line is going from one part to other, from B then to C, considering the point A fixed. So it is here like this, A to B, B to C, C to D, and again coming to A. So that means the vector is actually, the line is rotating, that is the circulation. Say that is the reason why this circulation is mentioned. So it is actually the rotation of this vector, right? That is the reason why this curl, as we know, the curl is the measurement of the angular rotation of any vector. So that is the reason why we are able to relate this line integral, that is a closed line integral, to the surface integral. What we need to remember is that Stokes law is applicable in all cases where we have to we are having any closed line, and that will be after the closed line. So we'll simply evaluate this in terms of the surface surface integral, right? So wherever we face any kind of problem where this line integral to surface integral or transfer from line integral to surface integral is required, or the vice versa, we'll apply this Stokes law. So after Stokes law, discussion about Stokes law, we are now going to discuss about this Laplacian operators. So this Laplacian operators, there are many problems. You might face different kind of problems where this Laplacian operator will be used to solve that kind of problem. So let us discuss the basic properties of Laplacian operators first, then we will go to the type of problems that we might face. So let us, for the properties or the characteristic of this Laplacian operators, we'll see that it is a scalar. This is a scalar differential operator. So this is the thing to remember. Scalar differential operator composed of gradient as well as divergence. So both operations should be there, gradient and divergence operators. That means in Laplace operators, suppose we have seen previously that we have operated either gradient or divergence separately. Now in case of Laplacian operators, we will use this gradient and divergence both together. So this is one of the property to remember. The next point, these Laplacian operators can operate on both scalar and vector quantities. Okay, so it can be used to calculation, or this can operate on both the scalars and vector quantities that we might have. And another thing, so if this operation is true, so we can write another property, Laplacian of any scalar. Suppose we are performing Laplacian operation of any scalar quantity, so it will always result in a scalar itself. So similarly, Laplacian of any vector quantity that we are using it, so the result will always be vector. So these are the properties. That's Laplacian of a scalar will always be a scalar quantity, and it is of a vector will always be a vector quantity, right? So now let us see how the representation things will occur in case of Laplacian. So Laplacian, we can write this Laplacian of any scalar field, suppose we take this as V. So this Laplacian of this scalar V will be expressed as, or rather is expressed as del square V. Now what is this del square V? Del square V is defined, this is, let us write, this del square V is defined as, this will be defined as divergence of the gradient of V. That means it is defined as divergence of the gradient of V. Okay, so that means all both divergence and gradient both we are using. So if we can represent like this, that means Laplacian of V, this field, will be equals to del dot del V, right? So we have gradient, this is divergence, this dot we have represent this dot as your but this is divergence. We represent divergence by this dot, and gradient there is no dot is there, so we are representing del dot del v. That means divergence of gradient of v, so that will be simply represented del square v. So both operations, divergence and gradient, are operated in case of this field that we are having v. Now if this field is, as I told you before, that if this field is a scalar one, if we operate this Laplacian of the scalar field, if this v is scalar, it will result in a scalar field. The result will be a scalar. And if this v is any kind of vector quantity, so after operation of this Laplacian operators, this result will be vector. So these are the basic properties of this Laplacian operators. So now we will see the coordinate, what in different coordinate system, what is the representation of different type of Laplacian operators. Let us see the representation of these Laplacian operators in different coordinates. Suppose we are writing in Cartesian coordinate system. It can be used for any different kind of coordinate systems like cylindrical and spherical that we have. Let us see what is the representation in Cartesian system. Others will be same, only the spatial variables will be different. So in Cartesian coordinates, Laplacian of scalar field v, suppose we are using the scalar field v, can be expressed as del square v. You know that this is why this representation del square is coming. So del square v will be equals to, so that this is actually the divergence of gradient of v. So that means we will use del x of ax plus, because it's a plus del y of ay plus del z of az, and product of dot del v del x ax plus del v del y ay plus del v del z. So this will be az. So this will be the representation of del square v. From here, therefore we can write del square v will be equals to del square, or double partial differentiation of del v del x2 plus del 2v del x2 plus del 2v del y2 plus del 2v del z2. So this will be the representation of these Laplacian operators in the vector system. And after this one, let us go to solving some problems, how to operate this Laplacian in different kind of problems. So let us now see what are the different kind of problems we might face and how to solve these problems. We are going to find out Laplacian operators of different functions that we might face. Suppose firstly we take the function, any vector is given as x square y plus x y z. So this is the problem, and we have to find out the Laplace. So some of the problem says find Laplacian operator of this kind of problems might happen. Find Laplacian operators of a function. So we will use, so what how to solve this kind of problem? We'll simply, the last equation that we had in our previous discussion, we'll simply use it. So we find out del square a of this vector that we are having. So, or maybe it may be scalar, so as per our definition. So we are not bothered about whether it is a scalar or vector unless they define it like that. Even if they define it, the process will be same. So del square a will be del x of del a del x plus del y of del a del y plus del z of del a del z. Right, so this is the function. So we'll simply write del x of the function 2xy plus yz del x of, since we are find out this del x of a is given as this, so I have find out this del x of a and I have put it directly here. So next we will find out this value we have already calculated. So in terms of del y, we will have this function as x square plus xz, and in terms of z we are having it at xy. So these are the functions. So simply after this, so we are simply operate this function, will calculate these differentiations. So we'll simply use, we'll have 2y as our answer, right? So this is one type of problem that you may face. This is, you can see that this problem is based on the Cartesian coordinate system. Now let us see another problem in some other different coordinate system, right? So this is the another problem. This is another kind of problem that we are having in other coordinate system. You can see here the space variables are r, theta and phi. So that means this problem, this is a representation of a function. This may be scalar or vector in case of a spherical coordinate system, right? So to find out this kind of problem can be solved like this. We will use this del square b as per the Laplacian equation. So we'll write this equals to 1 by r square, 1 by r square, 1 minute, 1 by r square del r of r square del b del r plus 1 by r square sin theta of del theta on sin theta del b del theta, right? Plus 1 by r square sin theta, sin square theta, again del phi of del b del phi. So this is a representation of the function in spherical coordinate system. So we will simply find out the values. This will be 1 by r square del r of r square 1 by r cos theta sin phi plus 2r phi plus 1 by r square sin theta del theta of minus sin square theta sin phi log natural of r, okay, plus 1 by r square sin square theta del phi of cos theta cos phi log ln r plus r square, right? So next, so this will be equals to 1 by r square cos theta. We are again using evaluating this differentiation again. So 1 by r square cos theta sin phi plus 6 r square phi plus by r squared sin theta minus 2 sin theta cos theta sin phi ln r plus 1 by r square sin square theta minus cos theta sin phi log natural of r. So this will be equals to, we will take 1 by r square cos theta sin phi, let us take it as common. So the remaining part will be 1 minus 2 log natural of r minus cosec square theta ln r plus 6 phi. So this will be your answer. So what we have done here, so actually we have represented this vector. We have calculated this r square db of dr first. That means this vector we have calculated in terms of r first, then we will calculate in terms of theta first. They again So in terms of phi, we will then evaluate. So simply I have put the values directly after the operation. Then after that, we'll use this differentiation of the total function again. We have to calculate this differentiation of this function which is coming here again. So we have, after this operation, we will simply take the common part here and leave the other parts. So this is the types. This is the way by which you can solve the problems in case of Laplacian operators. The problems are simple, just little bit of calculations required. Only the differentiation can be, actually we will use this differentiation function in 2 times. So all other things are same. So these are the example problems of Laplacian operators, right?